Welcome to the lecture on Chapter 6. So you spent time talking about linked lists, what you may or may not be used for. Now I want to start looking at, looking from Chapter 6 on, we're going to look at different data structures to help solve problems differently. Now that we have an understanding of linked lists and recursion, we can now look at ways of organizing data in such a way that allows us to process it and organize it for real-life applications. So we're going to look at a general topic of trees. So we're going to understand what a tree is. You can pretty much think of a tree as an organization chart. So that's kind of the picture you want to have in your mind and how we're going to process that. So we're going to look at understanding some basic terminology, some concepts, try to understand some different types of trees, like a binary tree, and what its basic attributes are. Look at different ways of traversing or getting through a tree. Look at there's two major categories. One is going deep, depth first, and then one going breadth across the tree as processing. And look at a couple of things I probably won't get into. I won't look at Huffman codes, and we probably won't look at examples. I'll leave the examples of parsing mathematical expressions outside of this. So just kind of keep it high level in general, since this is probably your first exposure to trees. So we're going to look at basic concepts, some terminology. So let's go through. Now, this is what I said. This is an organization chart. Well, you can kind of picture it as one. And it's a directed graph where each one of these are nodes, and each one has a different meaning. Now, the top part of this tree, this first node in this tree is called the root. Now, there are several terms that are used. Now, how I organize this tree is there are different levels, and as you can tell, as you go down to each set of siblings, or so you think of a genealogy tree, I guess, is probably even better than an org chart, where you got parents and siblings. So I've got B is a child of A, B, E, and F are siblings with each other. You've got external nodes, which would be C, D, G, H, I. An internal node, which would be something that has both a parent and a child, where E here only there's no children here, so it would not be an internal node, but just B and F because there's things above it. So these terms here, the last ones here with no children, are leaves on a tree. Kind of wish they wouldn't mix metaphors between parents and children and also you throw leaves in there. I'm not sure I know what you'd call these anyhow, but now you get each of these trees, and part is the way to solve some of these things. And this is where you start thinking, oh, I got a tree and I got a subtree. I got a tree within a tree, which all of a sudden gets you to start thinking about recursion. This is where one of the big uses of recursion. Maybe back in chapter 2 or 3 when we had recursion, you didn't think, how could I use this? Well, this is where recursion becomes key in making processing of these trees very easy to understand the algorithms. So you've got a subtree, and pretty much a single node can be a subtree. It just doesn't have any leaves or children associated with it. So just keep that in mind. So if I was going to, actually I'm not even sure this algorithm is a very good one, but it just converting a general tree, if you had mathematical, if you just want to put parentheses around it, so I'm not even going to go through it. But you definitely can see here, what am I doing? I'm convert to parm. the first thing I'm doing. I'm looping through. I am doing recursion, calling itself inside this loop over and over again to create this up. So it makes things relatively easy. Now, there's a special case of trees, and they're called binary trees. Binary trees have no more than 2 descendants. So when you looked at this here, F had what? It had 3 descendants. This is not a binary tree. A binary tree only has 2 descendants. And because there are definitely multiple different ways of traversing these, and we'll cover 4 of them. We'll cover 3 depth first and 1 breadth first traversal. So with a binary tree, you got subtrees just like I had before, and remember the rule is you can only have 2, maximum of 2. You can have less than 2. I mean, that doesn't stop this from being a subtree, but you just notice that maximum of 2 branches. So you got a left subtree, right subtree, and all of these are binary trees. Now, granted, what's this one? This one's a null binary tree. Nothing's been allocated, nothing's been assigned, but a single node can be a binary tree. The rule says no more than 2. So, again, no more than 2, no more than 2. Are they identical? No. But you've got this one's binary, binary. This one's binary. It's just that all I've got is, the right branches. That's the only way it goes. So all of these cases are binary trees, using the basic rule that there's no node that has more than 2 sub-nodes to it. Now, there's a concept of complete or nearly complete. And basically all that means is that at its lowest level, all the leaves are full. So here you got single node is a binary tree, and it's also complete because it's complete. There are no leaves, so that one's complete. A, B, and C, it's complete because all the nodes under A, there are no more leaves. Same thing with this one here. Now, nearly complete, here, binary tree again, only 2 nodes, but you can tell that underneath B and underneath C, not everything is filled out. So what you want to do is to show that something is a complete tree, you're looking at the lowest level and making sure that all the leaves exist. So in this case, my lowest level is 0, 1, level 2. I don't have component C. Node C does not have any children, so it is nearly complete. Get down here, it's boom, 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 and node is still not complete because I don't have that right node underneath that. So it's a nearly complete tree. Now, there's 3 ways of doing a depth first search. It is, I can do one, what they call pre-order. So basically it means what? I process the first one, I process number 1, then I go to the left subtree, then I go to the right subtree. I can do it in order. So that means I process, go to the left subtree, then process the node, the node 2, and then go to the subtree. Or there's post order, which means the node is the last thing. So I do the left subtree, right subtree, and then process this. They'll all give you the same solution, but it's the amount of processing time that it takes to do each one of these that you'll have to decide which one how do you want to go about doing it. So totally different ways of doing it. So let's look at the pre-order traversal of a binary tree. So it's basically, I process, since it's pre-order, I'm going to process the node first and then go on to the children, starting with the left and then going to the right. So my preconditions is I got a root with an entry node of a tree or subtree, like I said, tree or subtree. So what's that going to lead us to? That is going to lead us to recursion. And you look at this, it's you're thinking about how complicated, how big a tree could be, and this algorithm is relatively straightforward. So being a pre-order, I process the node first, so boom, process the root, and then I go to the left subtree, and then I go to the right subtree. And then this is where your recursion comes in. So I'm just going through, so it's a very straightforward algorithm. So if I look at the tree here that we had before, you had 2 subtrees. So what am I going to do? I'm going to process A, go to the left, process B, go to the left, process C, go back to B, go down to D. Go back up to A, go down to E, process E. There is no left, so it's a blank. And then there's no, go to E, there's a blank, and then go down to F. So you look at how you're processing, how you're walking through each of these nodes. It's A, B, C, D, E, F. So same sequence. I'm going to hit all the same nodes, but how I'm going to handle them and how I process them a little bit different. Here's just the same way looking at the way the subtrees are looked at and how using recursion. This is how you would call the routine. You know, process A, call the left subtree. Oh, recursion move said process B, call the left subtree, nothing, pack up, process D, back up E. So this is where you see recursion is going to be a big key. So now let's look at in order. So this is the same sequence. I go left node and the right sequence. So again, I call the left subtree, process the root, process the right subtree. The algorithm is fairly simplistic, all because of recursion. If you try to do this with a linked list or an array, it could be pretty difficult. So here's our same example here, and now I'm processing in order. So what do I got to do? I got to go to the left. Can't process that. Go to the left. Process C, process D, process C, then B, then D, then go back up, process A, then go down to the left, nothing, process E, process F. So that is how, so that in order, so I'm still hitting the same nodes, but what am I doing? Now you notice the order of the traversal is different. Hit all the nodes, covered them all, just the sequence in which they came out are a little bit different. And so now let's look at post order. So what's that mean? I'm going to do left, right, and then process the node. So the algorithm is fairly straightforward. Process left, process right, and then process the root. So when you look at this, what am I doing? I'm going process left, process right, go back up, process right, no left, process right, go back, process A. Again, I'm hitting all the nodes, but now my sequence of this is different. So just keep in mind. So it depends on which way you want to do it. Do I want to process this, the node you first hit? Do you want to do it first, in order, or last? And you decide which way you're trying to solve your problem that needs to be done. Now, I said we did 3 depth first. So depth first means what? I'm going to the, whoops, where'd my cursor go? I'm going down, I'm processing depth, going down as far as I can before I start working my way across. Well, the other method would be to do a breadth first search. That means I want to process A, then I want to process B, then E, then go back around and process E, C, D, and F. So I'm going to process each level in sequence. So I'm going to cross the breadth of the tree versus going how deep it is. So here you've got what? I'm setting the current node to the root, So now it's like, oh, what do we got here? I've got a queue, because I'm going to do what? I'm going to do first in, first out. When you processed post order, what did these look like? I'm popping things in, popping things off. So the depth first are stacks, whereas the breadth first processes as a queue. Now it's like, oh, making sense why we covered stacks and queues and linked lists and recursion before we got into some of the algorithms that could help you solve some of these problems in the future. So here I've got, you're creating your queue. I'm going to loop through my nodes until I'm not null. So I'm going to process the current node. Whoops. Hit the process the current node. I'm going to check if there's a left subtree. I'll put it in the queue. If it's a right tree, so it's not null, put it in the queue. Keep going until it's not empty, and you're just going to keep looping through each of the layers, and then once you're done, get rid of it. So basically, what am I doing? I'm going to put process A. I'm putting B and E in a queue. So boom, B, E, C, D, F in that order. So one of the ways that we've used have expressions, mathematical expressions, but this is one way that you could organize this mathematical equation and then process this in several different ways to get what your solution could be. If I did an infix traversal, what it could look like. But it's just basically same thing. What am I got? I'm just putting parentheses around information. So I am processing, I've organized it as a tree, and then I'm using it in sequence to process it. You could have done it postfix, and you could have done, your prefix. So some problems are just, you can organize your data in a tree structure, but in binary trees make it very simplistic to process. There are some fixed rules that can go through. Now, the question would be then is, how do I, if I don't have a binary tree, how do I insert, delete information in? And also, can I, since binary trees has some very standard rules, is there a way to convert a general tree into a binary tree so I can apply some of the routines we've just talked about? So here we've got a couple of different ways. I mean, I can insert first in, first out into a tree. So what's that mean? I'm going to, since I don't have a restriction of only 2, I can insert basically at the end of, the section. Or I can insert it at the beginning, last in, first out. So you can do it either first in, first out. So I'm going to process these in, and we're going to say, and it'll be the last one out. Or I can put it at the beginning and put it in. Each of them can be just depends on what you're trying to do. Now, sometimes in this, you may see a key sequenced insertion. And basically what that means is I want to make sure that the sequence that I'm inserting something into my tree in a way that it's still in order. So I have to make sure that it's either an alphabetical form or a numeric form. So right now you know that I'm going to be parsing this tree, doing comparison, and then making an insertion at the correct location. Now, if I've got a general tree, how do I convert it to a binary tree to take advantage of some of those routines we just talked about? Well, if I've got a general tree like the one we've got up here in the upper left-hand corner, now, first thing you want to do is identify all the leftmost children. So it's looking here and you say, here's B is the leftmost of A, C is leftmost of B, and G is leftmost of F. E has no leftmost, and neither do none of the leaves. So that's my first step. Second thing is I'm going to connect all my siblings. So I'm going to connect B to E, E to F, C to D, G, H, and I together. And then what I'm going to do is then get rid of any unnecessary links. So all the links that were there before, so I get rid of the one from B to D, I get rid of one from FH and FI, and all of a sudden you have the resulting binary tree. As you can tell, each one only has a maximum of 2 children, but now all my routines for binary tree now become the same. So identify the left, connect the siblings, so you're basically going across the level and connecting all of those siblings, and then go back and remove any unnecessary, unneeded links. Now, for your homework, I think this is the graph of first couple of homework assignments that I gave you, and I think that's the only one that I can give you a picture of. Yeah, we're not doing tree traversal for exercise 30, so should remove one more chart. So hopefully that gives you a rough idea of trees, kind of see where all the things we've talked about, linked lists, queues, stacks, recursion, all kind of start coming together to solve a case of a way to organize your programs. So hope it helps. If you have any questions, let me know. Talk to you later. Bye-bye.